In this section, we will discuss case history number 2, a multi-zone injector application. The multi-zone injector is located in the West Africa field in the North Sea region, and it's a 4-zone water alternating gas injector. And this was the first time an intelligent injector valve was integrated with the ICVs, the inflow control valves. 3 single-phase optical flow meters with pressure and temperature gauges were installed in 2004. And there were several objectives. One of the main objectives was to selectively inject water and gas into zones where it is needed most and to continuously monitor the injection rates. When needed, choke back the injection rates in the zones with high amount of water and remotely control the operation of ICVs and continuously monitor the sensor measurements with easy access. So all the details, results, and challenges on this case history were published in an SPE paper co-authored with the operator. And it was also presented in an SPE conference in 2005. So all the information is available in the public domain. The completion design was such that the zonal injection rates were obtained by subtraction of the flow rates measured by the flow meters. So here's a simplified schematic of the measurement system. We have 4 zones and 3 optical flow meters. The zones are designated by the blue color, zone number 1, number 2, number 3, and number 4. And the optical flow meters are designated by the red color, optical flow meter number 1, 2, and 3. So in general, the optical flow meters measure the total flow rate going through the pipe. So in this case, it will be measuring the commingled injection rates to zones below the optical flow meter. So let's go through this step by step. The optical flow meter number 3 will be measuring the injection rate to zone 4 directly, because there is only zone number 4 below the optical flow meter number 3. The flow meter number 2 will measure the commingled injection rates to zones 3 and 4, because those are the zones below the optical flow meter number 2. So the injection rate to zone 3 can be found by subtracting the flow meter number 3 rates from the flow meter number 2 rates. So in the case of optical flow meter number 1, it will measure the commingled injection rates to zones 2, 3, and 4. So the injection rate to zone 2 will be measured, will be calculated by subtracting the flow meter number 2 rates from flow meter number 1 rates. So how do we calculate the injection rate to zone 1? So that's basically subtracting the flow meter number 1 rates from the total injection rate. Now that total injection rate is a known value to the operator through some surface measurements. So here is the measurement system for a multi-zone injector application. So this application was the first time the optical flow meters were installed in the vicinity of inflow control valves. We have discussed this in earlier sections, but briefly, the inflow control valves create high acoustics. They are noisy completion elements in active use, so there is a chance that they may mask the flow signal. Indeed, that was the case for some extreme settings of the ICVs there was a negative impact on the flow signal from the flow meters. So we were, however, able to access the flow meters remotely and improve the data acquisition algorithms at the time. And at the end, all the flow meters became functional even at extremely high flow rates. However, this case history triggered the development of the acoustic tolerant version of the optical flow meter. So now, whenever there is ICVs involved in a compilation, we always recommend the use of acoustic tolerant version of the optical flow meters. After many years of operation, there was no loss of optical integrity in this system, and there was no report from the operator. From a value perspective, the injection rates as well as the cross-flow rates during shut-ins were measured successfully by the optical monitoring system. And the monitoring system improved the reservoir management. Based on the conversations we had with the operator, they stated that to achieve the same level of reservoir management without the use of optical monitoring system, they would need one additional well along with a frequent wireline logging program. The cost of an additional well is typically more than $10 million in 2004 standards. So the optical monitoring system eliminates the use of wireline logging program because it's a continuous measurement. It will provide the flow rates continuously in real time. So there is no need for a wireline logging program and intervening the well operations. So the logging program, wireline logging program became completely unnecessary. So the bottom line is that the optical monitoring system in this case history not only provided the injection rates and the cross-flow rates during the operation, but it eliminated at least one additional well with a significant cost. So it provided significant cost savings to the operator and completely eliminated the wireline program. So this was a huge success for the optical monitoring system.